Invite 6 people to a party. Any 6 strangers, friends, a mix. Now claim. Among them sit 3 who all know each other, or 3 who are all complete strangers. Not probably. Not usually. Every time. Forever. Try to design a 6-person party that dodges it. You will fail, and the failure is provable. With 5 people. Easy to dodge. 6 is exactly where escape becomes impossible. This is the smallest theorem about the inevitability of order. And it is the doorway to a subject where humanity's knowledge runs out at a shockingly small number. Turn the party into a picture. 6 dots the guests. Draw a line between every pair, 15 lines. Color each line. Cyan if the 2 know each other, magenta if they are strangers. Every possible party is now a coloring, 2 choices, 15 times, 32,768 parties. The claim becomes geometry. Every coloring contains a triangle of 1 color. Find 3 dots joined by 3 same-colored lines. The 1-minute proof. Pick any guest. 5 lines leave them in 2 colors, so at least 3 lines share a color. Say cyan, 3 acquaintances. Now look at those 3 among themselves. If any pair of them is cyan, done. That pair plus our guest is a cyan triangle. And if no pair of them is cyan, then all 3 pairs are magenta, a magenta triangle. Done. There is no third case. The triangle was never optional. Savor the structure of that argument. 1 pigeonhole, 1 case split, no computation. This is what mathematicians mean by elegant. The certainty arrives before the counting starts. Why not 5? Here is the escape. Arrange 5 guests in a ring. Neighbors know each other, a cyan pentagon. Non-neighbors are strangers, a magenta 5-pointed star inside. Check every triangle, 10 of them. Each uses at least 1 ring edge and 1 star edge. No triangle is all 1 color. The party dodges. 5 people can balance on this knife edge. A 6th guest anywhere breaks it. This pentagon and star coloring is up to relabeling, the only escape that exists, 12 disguises of a single desperate arrangement. The party puzzle has a love story inside it. Budapest, 1933. Esther Klein poses a challenge to her circle of young mathematicians. Place 5 points on paper, no 3 in a line. Show that 4 of them always form a convex quadrilateral. George Checkers attacked it for weeks, solved it, generalized it, and married Esther. Erdős named it the happy ending problem. Any 5 points, a convex quadrilateral guaranteed. For a convex pentagon, you need 9 points. For a hexagon, 17. Beyond that, like so much of Ramsey theory, the exact numbers are still unknown. Don't trust the elegance. Brute force it. All 32,768 colorings of the 6-person party, checked 1 by 1. Monochromatic triangles found in every single case. 0 exceptions. The rarest colorings manage to squeeze the count down to exactly 2 forced triangles. Never 1, never 0. Order is not just present. It has a minimum quota. The theorem survives elegance and exhaustion alike. Notice the shape of the distribution too. Most parties carry 4 to 6 forced triangles. Total harmony and total discord, 20 triangles, happen in exactly 2 colorings out of 32,000. Now climb one step. 4 mutual friends or 4 mutual strangers. How many guests force it? The answer is 18, proved in 1955. One more step. 5 and 5. Unknown. To this day, the answer is trapped between 43 and 48, and the number of colorings to check has more digits than atoms in your body. Erdős put it this way: if aliens demand R, 5, 5, or Earth, marshal every computer and every mathematician. If they demand R, 6, 6, attack first. How do you trap a number you cannot compute? From both sides. From above, a recursion. R of S and T is at most R of S minus 1 and T, plus R of S and T minus 1. The same addition rule as Pascal's triangle, so binomial coefficients cage every Ramsey number. For 5 and 5, the cage says, at most 48. From below, exhibit one clever coloring with no clique, a single certificate of disorder. The best-known certificate has 42 guests, 43 to 48. The gap has not moved in decades, 6 integers wide and unbreachable. The lower bounds hide a revolution. In 1947, Erdős asked, what does a random coloring do? Count the expected number of one-color cliques. If the expectation is below 1, then some coloring has none at all. You have proved a thing exists without ever constructing it. For cliques of 10, the arithmetic says random colorings stay clique-free well past 100 guests. This is the probabilistic method. Flip coins, take averages, and conjure objects nobody knows how to build. Half of modern combinatorics stands on it. And the pattern hunger goes beyond graphs. Color the numbers 1 to 4 with 2 colors. You can dodge any one-color equation A plus B equals C. 1 and 4 red, 2 and 3 blue. Safe. Add the number 5 and check all 32 colorings. By machine, every single one now contains a monochromatic A plus B equals C. Schur proved the general law in 1916. Enough integers force arithmetic to repeat a color. Graphs, points, integers, the substrate does not matter. Structure is compulsory everywhere. The party is a parable. Color the edges of any large enough structure, any way you like, and patterns appear that no amount of cleverness can prevent. Scatter points and some alignment emerges. Write digits and arithmetic progression surface. Ramsey theory's slogan, complete disorder is impossible. Chaos, given enough room, is forced to contain islands of perfect order. 6 people, 1 triangle, no exit. That slogan is now a whole branch of mathematics, and it started with a party puzzle. One ring of 5 that slips the net. One guessed more, and the net closes by a pigeonhole you can hold in your head, confirmed by a machine that checked every world. And one step beyond that, a question the whole species cannot yet answer. Between the trivial and the impossible, mathematics is thinner than it looks. Complete disorder is impossible.